Hello, everyone. Thanks for tuning in. I'm Marcel, and I'll discuss joint work with Tom, Subhayan, and Justin on quantum proofs of proximity. So this talk is divided into three parts. I'll begin by introducing the computational model that we'll be working with and relating it to some other well-known computational models. Then I'll move on to our results. So the first part of our results is about quantum algorithms or protocols that we construct and that fit into this model. And in the second part, I'll discuss some separations among complexity classes that surround this notion of quantum proofs of proximity. So let's begin with introduction and the familiar notion of the complexity class QMA. So QMA is the set of all languages that can be decided in polynomial time by a quantum algorithm that from now on I'll call the verifier when it receives help from an all-powerful but untrusted prover P. And this help comes in the form of a quantum state. Now, this picture generally leaves the prover implicit, but I'd like to argue that it's actually useful to have this explicit image of the prover in our heads. And this comes from the viewpoint of delegation of computation. So in delegation of computation, the verifier has some expensive computation that it wants to perform, but it would prefer to send it to the prover, for the prover to do the computation on its end, and then for it to send the answer in a way that the verifier can efficiently, cheaply check that everything was performed correctly. So I'll get back to this in a second, but for now, let me flash here the definition of the complexity class QMA, which if this is unfamiliar, I encourage you to pause and read carefully, but I'd like to just quickly go over what it means. This is the set of all languages that admit a quantum algorithm V, the verifier, that satisfies two conditions. One is that if it receives a string that is in the language, then there exists a proof that convinces the verifier of this fact. Whereas if the string is not in the language, then no proof can convince the verifier that it is with large probability. And the verifier here is bounded, which means in this case that it runs in polynomial time. But going back to that image of delegation of computation, if the computation itself can be performed in polynomial time without the help of a prover, then it makes little sense for the runtime of the verification to be also bounded polynomial. We like the verification to be much cheaper than the computation itself. So it makes sense here to have a more stringent notion of efficiency. And we can say here, for example, that an efficient delegation of computation protocol is one where the prover does polynomial time computation, but the verifier can check this computation in time that is not much larger than it takes for it to, say, read the input string. Okay, so if we can go back to quasi-linear time, and this is a meaningful notion that is useful, then nothing prevents us from saying, well, can the verifier be even more efficient? Can it run in sublinear time? But in fact, in this model, this is not true because there are simple languages that can be decided in linear time, but not in sublinear time. Although, of course, the notion of sublinear time computation is interesting. And this corresponds to the field of property testing. So now I'd like to show you what it looks like to have QMA in the property testing setting. Well, the main thing that changes in this picture is that now the verifier, instead of having explicit access to its input string, now it has query access to it. And we say that a protocol is efficient if both the number of queries that it makes to this string and the length of the proof that it receives from the prover are both sublinear. Although now we have to relax the notion of what it means for a verifier to decide a language. So the positive case still is the same, but now when a string is, we don't require the verifier to reject everything that is outside of the language. We only require it to reject strings that are sufficiently far from it. That is to say, strings that differ from every string in the language in a fraction of it, at least epsilon coordinates. Okay, so I'd like to just give a quick comment here that say that generally in property testing, we call languages properties and we denote them by the symbol pi. So we'll use the symbol in terminology from now on. Okay, so now that allows us to finally define the main protagonist of this talk, which is the class QMAP for quantum Marilyn-Arthur proofs of proximity. And this is a class of properties that is parameterized by three values. The first one, epsilon, is the distance from which we require the verifier to reject. So we can see that if epsilon gets smaller and smaller, this starts to look more and more like an exact decision problem. Whereas if epsilon is large, there are many strings in this gray zone that is between in the property and far from it, where the verifier can output arbitrarily. The second parameter is the proof length, which is the number of qubits in the quantum state that is sent to it from the prover. And the last parameter is the query complexity Q, which is the number of queries that the verifier makes to this input string in superposition. Okay, so that concludes the introduction. Let me move on to the algorithmic part of our results. So I'll first say that we make heavy use of the technique of amplitude amplification. And again, if this is unfamiliar, I encourage you to pause and read carefully. But what amplitude amplification allows us to do is to speed up a well-known classical procedure. So this classical procedure is the following. Suppose we have an algorithm that makes Q queries to its input and detects whether this input contains an error with some small probability rho. How can we make this algorithm succeed with high probability? Well, the standard way of doing that is just to repeat the algorithm 1 over rho times, roughly, so that then it succeeds with constant probability. What amplitude amplification allows us to do is to get a square root savings in this overhead. Instead of having an 1 over rho multiplicative overhead, we have only a 1 over square root rho overhead. Okay, so with that behind us, let me put all of that aside for a moment and discuss a simple but surprisingly interesting problem. So the problem is to verify whether a binary string has even parity with the aid of an untrusted proof. And let me remark here that this is not a property testing problem. What we'd like here is for a verifier that accepts strings of even parity if they get a correct proof and rejects strings of odd parity no matter which proof they receive. Okay, so how can we go about doing that? Well, it turns out that classically, there isn't really much we can do. If proof and verifier communicate an arbitrary amount in both directions, it still costs a linear amount of a linear number of queries for the verifier to check if the prover is not lying. This is because parity is a very sensitive function. Now, it turns out, surprisingly, that with a quantum algorithm, we can do better. So we can do that with a proof of length n to the power 2/3 and a number of queries that is roughly of the same order. Okay, so how can we go about doing that? Well, to do that, I'll first describe a vanilla randomized algorithm that in principle doesn't seem to do much, but as we'll see when we combine it with amplitude amplification, we do get something non-trivial. So this algorithm does the following. It receives some proof string pi, which is purportedly the parity of all of the blocks that comprise this our input string. So let's, for the sake of this example, say that the proof has length 3. So we'll think of this string as being divided into 3 blocks. So this is the first, the second, and the third. And now, if my proof string is, say, 1, 1, 0, this is claiming that the 2 first blocks have odd parity, while the last block has even parity. Okay, so now, since the proof is trying to convince us that the string X has even parity, then if the parity of the proof is odd, then we can just reject outright, because this says that the string itself has odd parity. Now, what happens if the string has even parity? Now we need to check that the proof is indeed correct, that it corresponds to the parities of each block of our input string. And the way we'll do that is we'll just sample some block uniformly at random, query the entire set of strings in this block, and check whether the parity of the block matches the parity of the proof. And in this case, it does, because both of them are odd. Whereas, say, if we queried the third block, we could see that this has odd parity, well, while the proof claims that it has even parity. And in that case, we would reject. Okay, so we can see here that if the prover cheats in a single block, then the probability that we'll catch the prover cheating is 1 over the number of blocks. And we'll use this in a second. Okay, so just to remind you of what amplitude amplification does, it takes an algorithm that makes Q queries and detects an error with some small probability and turns it into an algorithm that makes a larger, but not too much larger number of queries and detects an error with constant probability. So what we'll do is we'll just set the proof length to be n to the power 2/3 in this algorithm that we just discussed, so that each block has size n to the power 1/3. So that our algorithm makes n to the power 1/3 queries to detect an error with probability at least 1 over the number of blocks. And now if we plug these values into the amplitude amplification theorem, we can see that indeed the proof and query complexities are both of order n to the power 2/3 as we wanted. Okay, so although this doesn't in principle have anything to do with property testing, it turns out that a very similar strategy works for every property that is decomposable. So I won't have time to discuss in detail what decomposability is, but I encourage you to ask in the live event if you're interested. But decomposability is roughly what happens with parity. So parity, in order to check the parity of a large string, it suffices to check parities of many smaller substrings. So if a property has a structure that is roughly similar to that, then we can test it efficiently. And let me say here that when we go to the property testing setting, things become a bit more complicated because querying an entire block is already too expensive. And we would like to only query a few coordinates in a block. Now, since in the property testing setting, if there exists an error, then we're ensured that there exists many errors. There is at least an epsilon fraction of coordinates that are incorrect. We can use this to our advantage. But that still leaves the problem of, well, how are the errors distributed? It might be that the errors are all concentrated in a single block, or it might be that they're roughly distributed evenly across all blocks. And the fact that we don't know this distribution of errors creates an additional difficulty to make this work in the property testing setting. Okay, so just to give you a few examples of properties that fit this bill, this includes a host of properties, including functions that oscillate from non-increasing to non-decreasing at most k times. It includes strings that are accepted by some fixed branching program, strings that are generated by some fixed context-free grammar, or orientations of graphs that are Eulerian, for example. Okay, so before concluding, I'd just like to say a few words about the techniques that we use. For the decomposable properties, we build upon and extend known classical proofs of proximity. So these are objects that were introduced by Gruner and Rothblum and then built upon by both of them and Goldreich. And we show that, and they show that classical testers with a proof can do much better than classical testers without one. And what we show is that quantum testers with a proof can do better than their classical counterparts. And we also prove that there are properties that are not decomposable, but still admit a quantum speedup with quantum proofs of proximity. And this relies not only on the amplitude amplification algorithm, but also on the quantum element distinctness or collision finding algorithm of unbindings. Okay, so that concludes part number one. Let me move on to the complexity separations. So to do this, let me just remind you of what the polynomial time analogs of these complexity classes are. So if an algorithm is bounded and does some computation on its own, this corresponds roughly to the complexity class P. Whereas if the algorithm receives some untrusted proof, this can correspond to the complexity class NP. Whereas if proof and verifier can communicate bidirectionally, this corresponds to interactive proofs, or IP. Okay, so now when we go back to the property testing setting, when the verifier or tester is on its own, this corresponds to the class of property testers, which we call PT. The class of properties that are testable by a protocol where a verifier receives a non-interactive proof is the class MAP, for Merlin Arthur proofs of proximity. And when prover and verifier can communicate bidirectionally, this is IPP, for interactive proofs of proximity. And let me remind you that these classes, curly C, denote a set of properties. And these are all properties that can be computed with, all properties that can be tested with an algorithm in this model where the proximity parameter is a small enough constant and P and Q are polylogarithmic. Okay, so now when we go to the quantum realm, the analog of PT is QPT for quantum property testers. The analog of map is our protagonist, QMap. But let me also remark that there is an intermediate class between map and QMap where the verifier is quantum, but the proof is classical. And we call this QC map in analogy with QCMA. And of course, we can also define the interactive variant of such proof systems, which I won't discuss here, but I will have a few words to say about this at the end of the open problems. Okay, so now I can state the main theorem of this complexity theoretic part, which is that quantum proofs of proximity are larger than the sum of their parts. So this is the first of three separations that says that if we have both quantum capabilities and the proof, we can combine them in a way that is much more powerful than having either of them separately. The second separation says that sometimes quantum proofs are important. So even if the verifier is quantum, receiving a quantum state as proof is sometimes much more efficient than receiving a classical string. And finally, we show that even though QMaps are powerful, they're not too powerful. So quantum non-interactive proofs cannot substitute for classical interaction. Okay, so this is all summarized by this diagram, which again, I encourage you to pause and take a look if you'd like. But let me remark that, in fact, we prove something that is slightly stronger than the first statement. We don't only prove that QMaps are stronger than both maps and quantum property testers, we actually show that maps and quantum property testers are incomparable. So this downward arrow says that there are properties that are easily testable classically with a proof, but hard to test quantumly without a proof. And the upward facing arrow says that there are properties that are easily testable without a proof quantumly, but are hard to test classically even with a proof. And I'd like to dedicate most of the remainder of this talk to talking about the separation between classical testers with a proof versus quantum testers without a proof. Okay, so the strategy here goes through a strategy that has been very successful in the classical case. So this is the technique of getting lower bounds for property testers via lower bounds for communication complexity problems. So this was a technique introduced by Blaise, Brody, and Matulev, and it has been very successful ever since. But it turns out that this has not been applied to quantum property testers. And in fact, this was a question that was raised explicitly by Montanaro and De Wolf in their survey, and they were able to resolve with an appropriate application of error correcting codes. Okay, so just to briefly discuss, tell you what communication complexity and the disjointness problem are. In the communication complexity setting, Alice gets an n-bit string, Bob gets an n-bit string, and they want to compute some joint function of these strings by communicating the smallest number of bits in the classical case, or qubits in the quantum case, as possible. And the function that we're interested in here is whether there exists a coordinate that contains a 1 both in Alice and Bob's strings. And it turns out that this is a very hard problem. Classically, there isn't really much more that they can do except Alice sends her entire input to Bob, Bob computes it locally, and then sends the answer to Alice. But it turns out that it is also hard quantumly. We can get a square root speed up, but we're still bounded by a square root n number of qubits. At least square root n qubits need to be sent by a quantum communication protocol that solves disjointness. So I won't use this right away, but let me also remark that because this will be useful for the separation in a bit. It turns out that if Alice and Bob had a candidate coordinate, then that would be very easy to check. They can just send that same coordinate back and forth and check if they're both ones or not. So this will be useful in a moment. But for now, let me just at a high level explain how we can get lower bound, like how we can transfer hardness in communication complexity into hardness in property testing. So to do that, we'll assume that there exists some property that is efficiently testable and has two other features. One is that there exists a mapping that takes this pair of strings into the property if the strings are disjoint, but takes it far from the property if the strings are not disjoint. And the second feature that we'd like is that Alice and Bob can communicate a small number of bits to find out an arbitrary bit of this encoding of X and Y. Okay, so the strategy here is that Alice will emulate the tester on her end. So she'll execute the tester. At some point, the tester will ask for the coordinate for the bit at coordinate I1. Well, Alice doesn't know what that bit is, but you can communicate a few bits with Bob, find out what it is, and then tell that to the tester. And then the tester will execute, ask for a second coordinate. Alice will communicate with Bob, find out what it is, tell it to the tester, and this goes on until the qth coordinate, which is the last query the tester makes. Alice communicates with Bob, tells that to the tester, and now the tester says, okay, I accept or I reject. And Alice can use this answer to find out whether the strings were disjoint or not, because if the strings are disjoint, then the encoding is in the property, in which case the tester will accept. Now, if the strings are not disjoint, then the encoding is far from the property, which means that the tester will reject with good probability. So this means that by communicating C times the number of queries of this tester bits, Alice and Bob can solve disjointness. But we know that disjointness in the classical case has a linear lower bound. which means that the number of queries is at least n over c, roughly. And in the classical case, indeed, we can take c to be a constant, which gets us a linear lower bound for an interesting property. Okay, so that was the high level. Let me now instantiate this with what we use in our construction. So we first start with an error-correcting code over a large enough field. So we want this code to be linear, and we call this the distance of this code epsilon. And the property that we'll be interested in is a subset of all encodings. This is the subset of encodings of Boolean strings. And the main observation here is that a pair of strings is disjoint if and only if the encoding of their sum belongs to the set B. Because if they are disjoint, then we'll sum bit strings that have ones in different coordinates, which leaves the result a bit string. Whereas if they are not disjoint, there exists at least one coordinate I, where both xi and yi are equal to 1. So when we sum them, we get 2, which is a non-Boolean message, which gets us to the encoding of a non-Boolean message that is outside of B. Okay, so that means that we can use an epsilon tester for this property B to solve disjointness, as we discussed in a few slides ago. But let me just concretely say what Alice and Bob do in this case. So Alice has a string x, Bob has a string y. Alice uses this error-correcting code to compute c of x, and Bob does the same to compute c of y. Now, their goal is to emulate a query to this string c of x plus y. So what they'll do is they'll basically split it in half. Alice knows c of x, so she can compute this unitary in superposition. Now she'll send the entire quantum state over to Bob. And let me remark here that this is a superposition over indices in capital N. So we can do this with roughly log n qubits. Okay, so now Bob has the state, and since Bob knows c of y, he can implement the second unitary. And because the code is linear, this means that we can actually write this down as c of x plus y. And now Bob returns the state to Alice, and they've successfully emulated a single query of the tester. So that means that each query is simulated by roughly log n qubits of communication, which means that an epsilon tester that makes q queries gives us a protocol with q times log n communication complexity. But now recall that disjointness is hard even for quantum communication complexity. We have a lower bound of root n. And this means that both B and its complement cannot be tested with much less than square root n queries. And now the reason why I'll talk about the complement is that we don't only want this to be hard for testers, we also want this to be easy for classical proofs of proximity. And we take the complement here because it's easy to show when a string is non-Boolean. We just point to a non-Boolean coordinate. So now the classical proof will be just some coordinate, I and n, in which case the tester, the verifier, we will use two properties that certain codes have and that can be constructed, as was shown by Ben-Sasson et al. That is local testability and local decodability. So what the verifier will do is, first it will check that the string it has is a valid encoding, is some member of this code. If it is, then it will try to decode the ith coordinate. If the ith coordinate is non-Boolean, then it accepts, and otherwise it rejects. And this gives an efficient classical proof of proximity for this property, which proves the separation between classical proofs of proximity and quantum testers. Okay, so I'd just like to say a few brief remarks about the other separations. And again, if you're interested about these, please ask me in the live event. The first is the separation between testers and classical proofs of proximity, which comes from the property of forrelation. And in fact, Arison and Embinus, in their original forrelation paper, they show how this can be cast as a property testing problem. So using that, plus a few extra reductions, we can show that correlation is easy for quantum testers, but hard for maps. The separation between quantum proofs of proximity with a classical versus a quantum proof is essentially a recasting of a result that is known in the polynomial time setting. That is, there exists an oracle separation between QMA and QCMA, and we can just cast that in the property testing language to show that QMAP is different from QCMAP. And finally, to prove that interactive proofs are stronger than quantum non-interactive proofs, we use the permutation testing problem. Okay, so to conclude, I'd just like to say a few things about the obvious missing thing here, which is, well, how about quantum interactive proofs of proximity? They're certainly interesting, and both the polynomial time quantum variant and the property testing variant in the classical case are both interesting. And in fact, there is a very concrete question that we can ask here. It turns out that IPPs are very versatile. So we can test any language in a very large class of languages by using roughly square root n proof and query complexities. And it turns out that this is tight modulo some reasonable cryptographic assumptions. But of course, these cryptographic assumptions tend to break down in the quantum case. So this begs the question of, well, can we break the square root n barrier by having a quantum interactive proof of proximity in comparison to a classical one? Okay, so that concludes the talk. Thank you very much for listening, and I hope I'll see you at the live event. Thank you.